Hey, my name's Nate. I'm a software engineer at the WebAssembly team at Facebook. I'm here with Vlad, who's going to come up in a bit. He's also on my team. Our team's in charge of a lot of the web performance for Facebook. We work a lot on browsers to improve overall speed, and we also work on a lot of the core web infrastructure for Facebook with a focus on performance. Mobile web apps, kind of by necessity, seem to settle at around like one floppy disk worth of code. About 1.5 megabytes of code seems to be a pretty common trend that we're seeing across the mobile web. It's not just Facebook. Across the mobile web, we seem to have kind of all settled at the same amount of code or a similar amount of code. Additionally, the desktop web, we seem to have kind of all hit the same ceiling. Sites have hit a pretty common size for the amount of code that they have. Now, how do we get to this much code? So let's take a typical Facebook page. You have many different products actually within this one page. So you could have a video player that has different it's basically an entire kind of YouTube experience in this one piece on the site. And that maybe for this example, it's taking up 600 kilobytes. Then we could have basically an entire chat app. You have your friends. You can see who's online, who's not online. You can click. And every time you click, we immediately need something to open. You click your friend's name, that tab has to immediately open. We can't have kind of any lag or hit the network to load the code for the tab. So understandably, that can take about 1.5 megabytes in of itself. Let's take the Composer, for example. That's kind of a whole blogging platform that exists between the code to write different new posts, to comment on things. That can take up around 700 kilobytes. By itself, that's not crazy, but these things add up pretty quickly. We have search. You click on it, search suggestions immediately pop up with your friend's pictures, different things you want to look for. That can take up about 200 kilobytes. Again, not crazy by itself, but these things add up. And then we have these different tabs at the top of the page. Every time you click on one, we immediately pop up new results. There's kind of there's a little bit of room where we can load some more content in later, but we do immediately need to load something there when the user clicks on it. So the code for immediately loading stuff for that can take 600 kilobytes. And that's not even to mention kind of all the shared libraries and stuff. Combined with all of this, across the web, we've kind of hit a ceiling with how much JavaScript we can serve to browsers. Basically, everybody has kind of run into the ceiling with how much code we can ship. So let's look into what we do let's look into kind of why we hit that ceiling. And how this happened. So in this example, we're looking at the critical path for loading the site and kind of how it breaks down its different components. And this is data. This is kind of the average based on data that we collect from the wild. And like I said, it's the critical path. So it's looking at what steps block other steps from happening. It's not looking at total time overall. So we can see that about 30% of the work is on client time, and by that we mean time that the browser is doing work. We can see about 20% is on time that we're fetching JavaScript and CSS. And then we have network time and server time and time that we can't measure in this other category. But in general, we can see that about over 50% of the time that we're doing work, it's the browser that can be blocking stuff. So let's dig a little bit deeper into what the browser is doing. So of that kind of 50% of work, 25% of it is executing the JavaScript. We see about 25% parsing and compiling the JavaScript. Then we have time on style and layout, and then we have GC and CSS and paint. But overall, we can see 50% of the time that the browser is doing work, it's on executing and parsing and compiling JavaScript. That's a lot of work to do on every single page load, every single time you open a site. And then we also, we can be blocked on the browser cache every so often. For cache specifically, cache latencies don't really have kind of a nice distribution. So this is actually public data from Firefox, but we see similar numbers in Chrome. So the x-axis here, it's time buckets for different times, but it's important for how long it takes from when we request a file from the cache to when we actually start getting bytes. But it's important to note it expands exponentially, the scale on the bottom. And then the y-axis is just the number of requests that fall into each bucket. And it's interesting to note here, we don't really see like kind of a smooth distribution. Users can experience really quick loads, but they can also experience times when the cache will really block stuff from happening. And this happens more often than you would think, and more often than, and quite often it can actually block the page loading quite a bit. So all of this is really important because the web, it's a platform for applications, not just documents. We saw before like a big list of sites that have all hit the ceiling. It's not just Facebook. There's a lot of big applications that exist on the web, and it's really important that the web be a good platform for all of these applications. And Light and Go apps fit into this model too. On the mobile web, like the mobile web really fits the model for emerging markets really well. The mobile web, in a device that's constrained by maybe like memory, by network, the mobile web allows you to download code incrementally without committing to a full app to begin with. The mobile web is perfect for this kind of like emerging market world. Yet we still see companies like investing really, really heavily in Light and Go apps. And we would really like this to be a place where you can invest in the mobile web instead and just get an overall experience because it's more of a natural fit to build for the mobile web. So we really want to figure out like, how can we make large like applications work on the web? How can we like break out of the ceiling and allow kind of more people to develop on the mobile web instead of having to go to native platforms? So there's a few different strategies we can look at for dealing with code size. So one is shipping less code, and we do this very heavily on Facebook today. We already like load on demand as much code as we can for interaction. So like if you click on something, if we don't have to, we preload the code that we need to immediately show something when the user clicks on it, but other code that like can make the interaction better, like that loads later on the interaction. We also, about 95% of the modules that get loaded on the homepage are used in that load. And that's actually pretty good when we consider all the different experiments that are running at a time. Different product teams will add stuff. And the fact that we ship code many, many times a day, hitting that 95% efficiency is not trivial at all. We can also try to cache more code. But like I said, people move quickly on the web, and we ship the site multiple times a day. So these caches can often get invalidated. So part of like, there's a balance we have to strike between caching as much code as we can and also not invalidating code every so often. And then additionally, like the browser cache can sometimes add latencies of its own. Service Worker plays really nicely into this world too, but Service Worker still isn't there. Like Service Worker can still block requests that aren't going through it. It can add some latency there. Service Worker startups can still take time. Service Worker is absolutely the future, and we're like very excited for it, but it's not like quite there yet. It's getting close. And there's a whole other area too, where maybe the browser could do less for each byte. Maybe each time we like have a JavaScript byte, the browser could do less work, and that's something Vlad will talk about in a little bit. So speaking of Service Worker, I really do want to call out a lot of the recent optimizations that we've seen. Service Worker is really moving in a great direction, and we're very excited and grateful for a lot of the work that's been happening. I specifically want to call out like the work for ahead-of-time bytecode compilation. That's been huge. Preload was like transformative for us. It allowed us to ship many new experiences that we couldn't otherwise ship because we have preload now. A lot of the work around IPC and startup optimizations have been amazing. And all of these things we've been able to measure and like really see the results help us out like quite a bit. And we're very grateful. I'm excited about all the work going on here. Also, like generally, like the streaming parsing improvements have been great. Streaming compilation and more caching of bytecode at runtime. All of these things have been really great for us. We've been able to measure them, and they've all gone to contributing to allow us to like kind of break out that ceiling, kind of like raise the bar for how much JavaScript we can have and how big of an application and how like rich of an application you can have on the web. Cool. So now Vlad's going to talk a little bit about maybe some of the alternatives to shipping JavaScript.
Thank you, Nate. So Nate talked a little bit about some of the challenges we face with shipping a large application on the web, and really think of Facebook.com as a web application. And the challenge there is that we simply have a large application, and we need to have a large application. We want to build a sophisticated, engaging experience similar to native apps. So the issue that we face is that code size ceiling, and I think this is partly an artifact of current browser implementations and also some standards that we're constrained by. One issue that we keep bumping into is parsing overhead. Some people are surprised when they first hear about this, but parsing ends up being 20 to 30% of the main thread CPU time when loading Facebook.com. So it's very significant for us. And this is with, let's say 7 megabytes of JavaScript that we serve. And this is after doing code splitting and minification and intelligent packaging. And the fundamental issue is sort of the algorithmic complexity there. The parsing effort is proportional to the amount of code shipped to the client versus the amount of code executed. And on Facebook.com, we don't execute most of the functions or code paths. We do execute pretty much all of the modules that we serve, but we don't execute all of the code that we serve. So as a result, we pay this parsing cost for all the code, but we only ever end up using a fraction of it. And this is because JavaScript semantics, JavaScript spec requires that early syntax errors be thrown, which requires doing sort of a lean parse or a partial parse, syntax parse of all the JavaScript that's served. So we had some ideas for how to address this. And these are kind of a little bit radical ideas. And I want to go through all of them and kind of end up with a proposal. So the first thing we tried was, well, what if we didn't ship our JavaScript as JavaScript? What if we shipped it as a simple string? So obviously tokenization becomes simpler. You parse things on demand. And you basically just have an eval on demand. You replace your function bodies with an eval. So you defer parsing. So that's ugly for a lot of reasons. Eval is a security threat. Eval interferes with caching of bytecode. And we actually found it's not a perf when it's done naively, which kind of surprised us. And we believe the reason for this is that we have a lot of cold code, and there's also a lot of overhead from calling eval. And it's also not something it's not really the way you want to structure your site. But conceptually, that's kind of behavior that we want to end up with, where you only pay parsing costs for things that you're actually about to execute. And then, of course, we thought about WebAssembly. And I think this is sort of a best practice recommendation for websites that are serving very large apps. But it doesn't really work for us. And I think it doesn't work for a lot of websites. WebAssembly has really good performance characteristics, predictable performance and ahead-of-time compilation, allowing you to do more sophisticated optimizations on the bytecode generated, the WebAssembly bytecode generated. But the issue is that we actually have an untyped code base, a very large untyped code base, and a lot of other companies do as well. And generally, product developers don't want to do strict typing; they want to do optional typing. So that's kind of a big obstacle, and you can't obviously compile, dynamically memory managed language that's not typed to WebAssembly. There's other gaps there as well, like the expense of crossing between the DOM and the WebAssembly VM. So basically, we cannot convert Facebook.com to be a WebAssembly site. That interface with the DOM especially, we could theoretically output to WebGL or something, but that's a whole other can of worms that we don't really want to get into. I think WebAssembly is in some ways better suited for applications that are C++ like games that are shipped on the web. And WebAssembly itself also has some startup performance latencies, like it requires some validation and startup. So we thought about WebAssembly, and we'll probably end up using it in parts of our site. We already use asm.js for our video player, for example, and that has worked out really well. But we can't convert Facebook.com to be a WASM app. So some other ideas for dealing with our large code size. This is an old image macro, and basically what we did was we tried to build an interpreter in JavaScript and serve it a custom bytecode that's generated ahead of time. So this allows us to relax some of the semantics of JavaScript and allows us to apply some optimizations ahead of time. But it's basically a JavaScript interpreter written in JavaScript. It was written as an experiment by a developer named Sebastian Markovich, who works for Facebook. It was kind of an unusual experiment, I must admit, but we had some interesting learnings from it. It's obviously optimized for JavaScript cold starts. There's no parsing or compiling for code you're not using, or no compiling at all because it's an interpreter. It tried to integrate as much as possible with the existing JS environment, so obviously the existing GC, the object model, and the standard library. It was actually very feature complete, so it passed most of the Test 262 conformance suite. Just a few edge cases that we didn't care about did not pass. Had try-catch support, strict and non-strict modes, seamless transitions, but obviously you missed out on a few things because it was not a real VM. It was basically a JS interpreter written in JS. It had no jitting, it had no inline cache, and also suffered from expensive array bounds checks because the memory model used was essentially a large array, and that adds up when you're doing a lot of array accesses. So what were the performance numbers that we saw? We saw, first of all, that this interpreter is very small. The initializing JavaScript module became twice as fast. This is the work necessary to initialize all the thousands of JavaScript modules that we serve on the Facebook newsfeed. This isn't unsurprising because, again, costs are now proportional to what's actually used. But of course, some costs were prohibitive. The bytecode became larger after compression, even though it was smaller before compression. A benchmark that we had, which is Hacker News implemented in React, became significantly slower. Hot loops were slow, and React core library code was, again, prohibitively slow. So what were our conclusions from that? So first of all, many of our code paths are executed only once or never. So it's kind of our workload. This WebVM, as it was called, was a lot faster for cold code than native V8 implementation. And ideally, to make this an approach like this work, we would have to have an understanding of which code is hot and which code is cold. And that actually is possible for us. We could figure that out based on field telemetry, but we wouldn't really have a way to use it unless we deployed an approach like this WebVM. So that's one of the ideas we had for perhaps trying to bring down that parsing cost so we can build a larger and richer application. So I think a more reasonable approach is to simply relax the JavaScript semantics a little bit. And this is a new proposal that we have called binary AST. I'm sure many of you have heard about it. It's basically a binary encoding for JavaScript that allows you to do lazy parsing. So it's the same old JavaScript grammar. It's not bifurcating the language, but it has a few annotations that allow you to selectively parse only what you need when you need it. So we're working on it with Mozilla. We're implementing it inside Mozilla's SpiderMonkey JS engine. We're also working on it with a person from Bloomberg. And we're presenting it to TC39. And very soon we'll be able to announce some end-to-end performance numbers. So we think this is a potential way to really bring down that severe parsing costs and really make costs proportional to, well, basically proportional to what they should be, which is how much code is being executed. And if you're curious about the project, you can check it out on BinAST A. There's an explainer document in one of the sub repos, and there's also a preliminary implementation. So those are some of the ideas, experiments that we have done to try to bring down that parsing cost. But I would also like to mention a few updates from our little web speed team at Facebook. First off, we have a new proposal for profiling API. This is a native profiling API. If you guys attended the last BlinkOn, you might not remember our presentation that talked about us implementing a JS profiler in JavaScript. And I think you guys can kind of see a pattern emerging here. And we found that very useful, but unfortunately we lost that JavaScript profiler, in-page JavaScript profiler, when shared array buffers were disabled from the web platform. But we found it extremely, extremely useful while we had it, and we would really like to see a native implementation of a profiling API. This will allow us to understand how our code performs in the field on actual user devices and allows us to identify any bottlenecks or hotspots or code that's running when it shouldn't be running and draining battery. So basically this would really revolutionize how web developers could debug performance problems of their sites. So we're going to post an explainer in the WICG repo very soon. And there's one more update from this team. We have a new focus and a new mandate to do more browser engineering. And we will be contributing code to Chromium. In particular, we're interested in contributing to the cache and service worker and maybe looking a little bit into V8 and parsing as well. And of course, we'll be doing more standards work, such as this native profiling API. Thank you. If you guys have any questions about either what I said or what Nate said, there's a yellow microphone right there. So we have a little bit of time. All right. First question.
Hello. Great presentation. It was really interesting data. And I'm super excited to have you all contributing to Blink and Chromium. How do I put this? I like the idea of like divorcing JS execution performance from just the raw size of your JavaScript file. But it was interesting to me that you talked about Lite and Go apps, because those require also not loading a lot of stuff over the network, as those are typically in markets that have a large like 2G and 3G set of users. Do you have thoughts on how to merge like dealing with network size and the rest of this sort of like the binary AST thing and that sort of thing?
So just for the binary SD aspect, binary SD I think is roughly, at least the numbers we have right now is roughly on par with JS size, so there's not really a size trade-off. But I think Nate does have some good thoughts about the Light and Go apps and how they can be better served by web apps.
Yeah, I mean, like Light and Go specifically, they're still bigger than like the amount of JavaScript that we're shipping. So like with service work and other stuff, like I really do think that like the web is like a better opportunity because it lets you like ship less code than you otherwise would. But like we've kind of hit the ceiling because we pay a parse and compile cost on every single load, where a Light or Go app, like you pay it once when you like ship the app to the app store and like build it. But every device isn't paying that cost when the code loads. So you're able to ship a little more code and have it run performantly. But like ultimately, the web, I think like the code size would still be smaller than a full native app. So I still think it would be like the better way to go if we can like enable people to ship enough code where they can make a competitive experience.
Yeah, thanks. Yeah, I think there's basically a couple ingredients there, like the fact that you can cache, but you only cache things that you've actually used, and only stream the functionality you need over the network, so you don't have to install a large footprint app, and not repeating the parsing work across 1 million devices or 1 billion devices. Yeah. Other questions?
So we've been talking about speed a lot. Is memory use actually a metric that you track?
Yes, it is. It's something that I'm working on currently. So we have noticed that Facebook does suffer from some memory leaks. And I've built, we have an extension that's deployed internally at Facebook called the Site Speed Monitor. So it's deployed to our employee population, which is sizable these days. And it basically is able to access some of the more privileged extension APIs, such as the tracing API or the DevTools debugging API, to understand how much memory is being used in a precise way. And then if too much memory, Facebook.com is using too much memory inside an employee's browser, Chrome browser, it will capture a snapshot and a heap allocation trace and then report it to a central location where then I go in and analyze it. And we use that to find big leaks and to also characterize the patterns of memory usage. The work that you guys are doing with the Windows Performance Memory API, I think is very, very valuable, and I'm really looking forward to like that more precise memory footprint measurement. And we've talked to the VA team, and we participated in the Memory Roadshow. We are definitely keeping an eye on that, and there'll be more announcements and more work happening soon. More questions? Okay, thank you guys.